Before we start looking at the last of our momentum topic for this semester, I want to just remind you of what we're doing on Thursday. There will be a review of all the material that we have covered this semester. Now, this is going to be on Blackboard. This is not going to be on YouTube because it's quite long, and I'm going to have to post it in a couple of parts probably. So you will find it on Blackboard if you are one of the people that has just followed my channel and go there every class day. Additionally, I will have all of the specifics on the final exam on Thursday as well. We'll talk about the date, time, format, all of that sort of stuff on Thursday. So that's what we'll be doing then. Today we're going to finish up conservation of momentum and impulse momentum relationships by looking at some problems out of the back of chapter 9. And the first one that I want to look at is problem number 35. Problem 35 says that we have an amateur skater that is stranded in the middle of a skating rink. And that the skater, while she tries to move, she just slips around because she's not wearing skates. She's just wearing regular old, like, tennis shoes. And she slips and slips, but she always ends up just staying in the same place. Well, what that means is that the ice, being very slippery, there is no friction. And if you remember, static friction is what makes it possible for us to walk across a floor. So she's stuck. Well, she gets this idea. So she takes off her gloves and she pitches them as hard as she can, which turns out to be 3 meters a second, which doesn't sound very fast, but it can be difficult to throw something lightweight at a very, very fast speed. And the question asks us, will she move if she throws her gloves to the right? And the answer is absolutely yes, from conservation of momentum. We start with the person and her gloves both having a speed of 0 meters per second, so they have 0 momentum. If the gloves gain a positive momentum to the right, the person has to then have a negative momentum that points to the left so they can add to 0 again. So absolutely, she's going to move off with some velocity. It's probably going to be kind of small, but it's not going to be 0. So let's apply our conservation of momentum relationship. The initial momentum of this system of interacting objects, the person and the gloves, is 0. So the final momentum also has to be 0. So the person has negative momentum, they're going to move to the left. The gloves have positive momentum, moving to the right. So let's solve for the velocity of the person. And that's going to be 0.042 meters per second to the left. It's pretty small, but eventually, with no friction, that will be a constant velocity. She will get to the edge of the skating rink, and then she can walk around to the other side of the skating rink, pick up her gloves, and go home. Last Thursday, we were talking about conservation of momentum in terms of collisions. And we said that there were kind of 3 basic types of events. The event is the thing that separates the before time from the after time. And in the previous examples we looked at, these were collisions, things coming together. But they don't just have to be collisions. The events can be a separation, like we see in this example, a throw. So if we have elastic, inelastic, and perfectly inelastic events, what kind of event would this be? Well, we can look at it from a kinetic energy standpoint. The initial kinetic energy of this system is 0 joules. And the final kinetic energy, which is the kinetic energy of the two objects added together, is 3.2 joules. Now, even though the person is moving to the left and has a negative velocity, kinetic energy depends on velocity squared. So negative values squared are positive, and so what this means is that we have gained kinetic energy. Kinetic energy is not conserved. So it's either inelastic or perfectly inelastic. Well, the perfectly inelastic examples happen when the objects are attached at one point and have the same velocity. In the examples we looked at last Thursday, this was a final velocity situation. Two objects came together and they stuck together for whatever reason, and they had the same final velocity. Well, in this example, we have two objects that are attached and have the same initial velocity. So this is also an example of a perfectly inelastic event. Well, instead of losing kinetic energy, the system has gained kinetic energy. And where does this come from? Well, this was chemical energy stored in the body of the skater that is transferred from her or converted from her into the kinetic energy of the system. So total energy in the universe has not changed, but the kinetic energy of the system has increased. It's gone from stored chemical energy into motion energy. Next problem I want to look at is problem number 37 out of chapter 9. And in this problem, we have a 60 kilogram person that is running along at 4 meters per second, and they step onto a 120 kilogram cart that is initially at rest. And then the cart is going to move forward. But when the person steps on the cart, they don't just instantly come to rest with the cart. They slide along the top of the cart for a little bit. And eventually, the person and the cart will come to the same velocity. So let's look at this from a conservation of momentum standpoint. We're going to look at before the person contacts the cart and when the person and the cart come to the same velocity. So before the contact is made, the total momentum of the system is just the momentum of the person, which comes out to be 240 kilogram meters per second, or that can be written as Newton seconds. Once the person and the cart come to the same velocity, the momentum at that time also has to be 240 meters per second. So the mass of the person plus the cart times their final velocity equals 240 meters per second. We can solve for that velocity, 1.33 meters per second. And this is part A of this problem. Now the next thing we're going to look at is actually the collision process. When the person steps on the cart that has 0 speed, and the person is actually going to slide across the cart. A force of kinetic friction between the person's feet and the cart is going to bring the person and the cart to rest relative to one another. In other words, they're going to end up at the same speed. Now, one of the things that we haven't looked at in our conservation momentum examples is what happens sort of during that collision. we say, this object has an initial speed and that object has a different initial speed, and they come together, they collide, and they end up with the same final speed. But we don't talk about what happens from the moment of contact until they actually end up with the same final speed. And that's what we want to look at in this particular problem. So the collision, the event that separates the before time from the after time, is what happens when the person hits the cart and they slide across the cart with a force of kinetic friction. So here we have the person on the cart, and there is going to be a force of kinetic friction between the person's feet and the cart surface, and it points in the opposite direction of the person's motion on that cart. So it points to the left and the person's moving to the right. But from Newton's third law of motion, we know that there's also a force of kinetic friction from the person's feet on the cart that points in the opposite direction. It points in the forward direction, or in the plus x direction. And this is the force that actually gets the cart moving. This is the force that provides the acceleration for the cart. Well, the force of kinetic friction is equal to the coefficient times the normal force on the person. And the normal force, in this case, is going to have the same magnitude as the weight of the person. And we're told in the problem that the coefficient of kinetic friction is 0.4. So we can solve for the force of friction. It's 235 newtons. And now they ask us, how long does that force of friction act? What's the length of time that basically the person is sliding across the top of the cart? Well, from the impulse-momentum relationship, we know that force multiplied by time equals the change in momentum. In this case, we're talking about the change in momentum of the person. So we're talking about the kinetic friction force times the time it acts equals the change in momentum of the person. So the time comes out to be 0.68 seconds. Now you can see here that the final velocity of the person is not 0. It's 1.33 meters per second. So don't assume that the person comes to rest, because they don't. All right, so here are the things we have learned. The final velocity of the cart and the person, 1.33 meters per second. The force of friction that acts on the person and the cart during the collision event, the time it takes to go from having this initial velocity for the two and this final velocity for the two, 235 newtons, and takes a time of 0.68 seconds. So let's keep going here. There's more to find out about. But we can write out all the stuff we've learned so far. Now what they want us to find is, let's look at the change in momentum of the person. And the change in the momentum of the person is equal to the final momentum of the person minus the initial momentum of the person. But it's also equal to the force of kinetic friction times the time that force acts. So the change in momentum of the person is negative 160 newtons per second. And while I did not do the mass times change in velocity example, you should do that yourself and verify that you get the same number. Now let's find the change in momentum of the cart. Well, the initial velocity of the cart is 0. So the change in momentum is just equal to the final momentum of the cart. And we get that it's positive 160 meters per second. This is part D. So we find that the change in momentum of the person is negative the change in momentum of the cart. The person loses 160 newton seconds of momentum. The cart gains 160 newton seconds of momentum. Momentum of a system of interacting objects is conserved. All right, now what we're actually going to look at is we're going to look at this from a standpoint of work and energy. So let's start at the very instant the person's foot or feet first hit the cart. And I'm going to mark the position of the person and the end of the cart at 0 meters. And then we're going to look at what happens as the person slides across the cart until the person comes to rest with the cart, and they both have a speed of 1.3 meters per second. Well, let's look at the distance these two objects have traveled. The cart has traveled this distance d, but the person has actually traveled a longer distance because of the fact that they are sliding across the top of the cart. So they travel two different distances. Well, let's look at the work done by non-conservative forces on the person. That would be the work done by the kinetic friction force that acts on the person. From the work energy theorem, that's equal to the change in kinetic energy of the person. So we have this frictional force that acts along over that distance that the person travels equals the person's change in kinetic energy. So let's solve for the distance that the person moves. That's 1.81 meters. We can do the same thing for the cart. The work done on the cart by non-conservative forces is equal to the change in kinetic energy of the cart. Well, the force that does the work is a kinetic friction force. And it's pointing to the right, and the cart moves to the right. That means the kinetic friction force is actually doing positive work. Kinetic friction is a non-conservative force, but it doesn't always do negative work. In this example, the kinetic friction force is doing positive work. That's why the cart has an increase in kinetic energy. So let's solve for the distance the cart moves. That is 0.454 meters. So when we look at this, we have the same force that acts on the person as acts on the cart. But it acts on the person for 1.81 meters. That's a longer distance. And it acts on the cart for 0.454 meters. That's a shorter distance, which means the work done by friction on each of these objects is not going to be the same. So now let's look at this from a change in kinetic energy of these two objects. So the work done by friction, which is equal to the change in kinetic energy of the person, is negative 427 joules. So what this means is that the person gives up 427 joules of energy because of friction. Now let's look at the change in kinetic energy of the cart. The cart gains 106 joules of kinetic energy. Well, the person gave up 427 joules, but the cart only got 106 joules of that energy. Where did the rest of it go? 321 joules of energy became heat energy or thermal energy in the feet of the person and in the cart. So kinetic energy is not conserved here. So if we were to ask what kind of collision is this, what kind of event is this, and this is a collision, here we have two objects with different initial velocities, but a common final velocity, and kinetic energy is not conserved. This is totally a perfectly inelastic collision. Okay. Okay, the last topic that I want to talk about is related to the reading for today, which was section 9.9, I believe, the one on rocket propulsion. We have talked about change in momentum, which is equal to change in mass times velocity. And all of the examples we've looked at so far, we assume that mass is constant and velocity is the thing that changes. But it doesn't have to be that way. We can have a change in momentum because we have a change in mass with a constant velocity. Or we could have a change in mass and a change in velocity, which is a much more complicated situation. Now, most of the time when we are looking at two objects in an isolated system that are interacting, it's usually the change in velocity that's happening and not the change in mass. But, as in the example of rocket propulsion, the rocket expels fuel as it moves, and so the total mass of the rocket fuel system decreases with time. Another example of this would be if you take an ice cube and you slide it across a countertop. What you find is that the contact between the ice cube and the countertop melts the ice cube a little bit, and it leaves behind a trail of water. So the mass of the ice cube is actually decreasing with time. So let's take a look at an example where we have a change in mass for a particular object. And this is problem 52 out of chapter 9. And in this problem, we have a conveyor belt that is moving on frictionless rollers. And the velocity of the conveyor belt is a constant 0.75 meters per second. Now, onto that conveyor belt, sand is being dropped from a hopper. And this could be, say, in a glass factory where sand is being transferred to a kiln for melting and making glass. The rate at which mass is being added to the conveyor belt is 5 kilograms of sand every second is dropping onto this conveyor belt. So the mass of the conveyor belt, the mass of this system, is increasing with time, but the velocity is staying constant. So the first thing they asked me to find is the rate of change of momentum of the conveyor belt. So that's the change in momentum with time. So change in momentum divided by time is final momentum divided by initial momentum over time. But the velocity is constant, but the mass is changing. And the rate of mass change is 5 kilograms per second. So I get a change in momentum of 3.75 Newton seconds per second. Well, the change in momentum of the conveyor belt from the work impulse equation is equal to a force acting on that conveyor belt multiplied by the time the force acts. This is an external force provided by a motor. And so we have change in momentum over time equals the external force multiplied by time. And you divided both of those by time. So we find that this external force has a value of 3.75 newtons. This is the second thing they ask us to find, is the magnitude of the external force. So the change in momentum with time, the rate of change, is 3.75 newtons, or Newton seconds per second. That's also equal to the external force. Well, I also want to look at the speed of the conveyor belt, 0.75 meters per second. That means that the distance that this conveyor belt moves is 0.75 meters every second. Duh. So let's find the work done by this external force. Well, in 1 second, this 3.75 Newton force moves the conveyor belt 0.75 meters. So the work done by the external forces, the external force, the motor, is 2.81 joules per second. So this is the next thing they have asked me, is find the work done by the external force. 2.81 joules every second. Now let's look at the change in momentum of the sand with time, the rate of change. The initial speed of the sand in the hopper is 0. So this is just the final speed divided by time. The final momentum divided by time. And that is the mass of the sand dropped per time times velocity. So we get 3.75 Newton seconds per second. Well, again, the change in momentum of the sand divided by time is just the force that acts on the sand to make that change, and that is a kinetic friction force. Because when the sand hits that hopper, when the sand hits the belt, it doesn't instantly come to a final speed of 0.75 meters per second. Much like the person colliding with the cart, there's a kinetic friction force that acts, and that's the force that's responsible for its change in speed. And it turns out to be exactly the same force as the external force. Okay. So we have the same force acting on the sand. Now we want to find the work done per 1 second by that kinetic friction force on the sand. And the work done per second is equal to the change in kinetic energy of the sand per second. And we get the work done by the kinetic friction force on the sand is 1.41 joules per second. Again, we don't get the same work done on the sand as the work done on the conveyor belt. And this is very similar to the last problem that we had in some respects. We have exactly the same force acting on two different objects. Now, this is not a result of Newton's third law of motion because we are not looking at the friction force that acts from the sand onto the conveyor belt. But it's still the same magnitude force. And yet, it does a different amount of work. So the motor does work of 2.81 joules per second on the conveyor belt. In other words, that's the energy the motor is transferring to the conveyor belt every second, 2.81 joules. But only 1.41 joules of that becomes the kinetic energy of the sand. So where does the difference in energy go? Because remember, work is change in energy. Well, that difference in energy becomes thermal energy in the sand and the conveyor belt because of the kinetic friction force that's acting between the sand and the conveyor belt. So if we were looking at this example, what kind of collision would you call this? Well, again, this is a perfectly inelastic collision between the sand and the conveyor belt. They have different starting speeds, but they have the same final speed with different changes in kinetic energy.